In this video, we're going to continue to focus on the preparation of organohalides from alcohols, and we're looking at some of the details of the SN1 mechanism.
So here we have, for example, the reaction of T-butyl alcohol with HCl to form T-butyl chloride with water as a byproduct. And as we saw in the previous video, the rate is equal to a rate constant K times the concentration of the alcohol. And so the concentration of the HX does not affect the rate of the reaction. So we need to have a mechanism that can explain how this reaction works and that is consistent with this experimental evidence. But it's also important to keep in mind that a mechanism can never be proven. We can collect evidence that supports a proposed mechanism, but it's always possible that somebody designs a new experiment that disproves a particular mechanism. So what we're going to talk about throughout the year will be mechanisms for which there's a lot of evidence that supports it, but we never want to say that it is a proven mechanism. But here we have what's a generally accepted mechanism for the reaction of a tertiary alcohol with HX. So in step 1, we have our T-butyl alcohol reacting with HCl, and the alcohol can act as a base, grab off a proton from HCl. These electrons move on to the chlorine, giving the protonated alcohol. So this is the hydrogen that was originally present, and this is the hydrogen it just grabbed from the HCl. The oxygen still has one lone pair, but now it has a positive formal charge, and we also have chloride, which has a negative formal charge. So this step is just an acid-base reaction. Step 2 involves the protonated alcohol, and the pair of electrons shared between the carbon and the oxygen can move onto the oxygen. This gives us, I'm going to write out just a bit more detail for a moment. We have this, and we have water, two lone pairs, so that oxygen has no formal charge, but this carbon only has a total of 6 electrons. It doesn't have an octet, and when we count for formal charge, it owns 1, 2, 3 electrons, and so this carbon has a positive charge. So this is called a carbocation. It's a cation on a carbon. So in this step, what's happened is that a leaving group leaves. And now in step 3, we have our carbocation, and it can react with chlorine. So remember, we made chlorine here. Now this chlorine can come back and react. So the chlorine acts as a nucleophile, shares its electrons with the carbocation, which is the electrophile. And so we have a new bond between the carbon and the chlorine. The chlorine still has its 3 lone pairs. The carbon is still connected to the 3 CH3 groups, and we've gotten to our product. So this reaction occurs in 3 elementary steps. So an elementary step refers to, it could be part of a mechanism where between reactants and products, there's only a single transition state. So a reaction could involve a single elementary step, or it could involve multiple elementary steps. This mechanism involves 3 elementary steps. The first one is an acid-base reaction. The second one involves the leaving group leaving, and then in the third one, we have nucleophilic addition. Here's our nucleophile adding to our electrophile. If we look at this mechanism overall, keep in mind our starting materials are the alcohol and HCl, and so that's what we have here. And our products are T-butyl chloride and water, and so here's our T-butyl chloride, and here is our water. So this is an intermediate. It's produced in step 1. It's consumed in step 2. This is an intermediate that's produced in step 1 and consumed in step 3. And this is an intermediate that's produced in step 2 and consumed in step 3. In addition to our overall reactants and products, we can think about the products of step 1, the reactant of step 2, and the products of step 2, the reactants of step 3, and the product of step 3. Another part of the proposed mechanism is based on the slow step of the reaction. So here we have an acid-base reaction, so those are pretty quick. Here we have something that is electron-rich reacting with something that is electron-poor, so this seems like it would be a pretty easy reaction. But here we're going from a species that has a positive charge on oxygen, but oxygen still has an octet. But in the product, we have carbon without an octet. So this is going to be very unstable. And since this is unstable, this is probably going to be a difficult step to carry out. Another thing that's important to keep in mind is that atoms form bonds to be more stable. So the process of bond forming releases energy, but the process of bond breaking requires energy. Here we're both forming and breaking bonds. Here we're only forming bonds, but here we're only breaking a bond. And so this is going to require a large input of energy because it's only bond breaking. There's no bond forming to go along with it. So part of the proposed mechanism then is that this is the slow step or the rate determining step. So with the rate determining step, this is the slow step that controls the rate of the overall reaction. So this reaction proceeds through the SN1 mechanism. S for substitution, because overall that's the change that happens. The OH is replaced by Cl. Nucleophilic, because the nucleophile adds to the electrophile. And the 1 stands for unimolecular. Unimolecular because in the rate determining step, there is only one molecule in the transition state. So we give a number to the mechanism based on how many molecules are in the transition state of the rate determining step. So SN1, substitution, nucleophilic, unimolecular. Finally, this mechanism is consistent with the experimentally observed rate law. According to the rate law, the rate of the reaction only depends on the concentration of the alcohol, not on the concentration of HX. Well, if this is the rate determining step, then this is the only molecule that is involved in the transition state of the rate determining step. So only this molecule should appear in the rate law. So it's consistent with this experimental evidence as well. So let's break down these steps a little bit more. Step 1 is proton transfer. So we're just talking about an acid-base reaction. So here we have our alcohol plus HCl reacting to form the protonated alcohol plus Cl minus. And so the oxygen is grabbing a proton. So we're talking about an acid-base reaction, which means we need to think about pKa values. So hydrochloric acid has a pKa of negative 3.9, and protonated T-butyl alcohol has a pKa of negative 1.7. And so this is the stronger acid with a smaller pKa, therefore equilibrium lies to the right. Now, what does that mean as we translate this to an energy diagram? Well, let's say this is the energy of our alcohol plus HCl. The fact that the equilibrium lies to the right, that means that the product of this step must be lower in energy. So this is our protonated alcohol plus Cl minus. And then there will be a transition state leading to this. So at the transition state, we are somewhere in between. So the oxygen is starting to form a bond with the hydrogen. The hydrogen-chlorine bond is breaking. The chlorine is picking up a partial negative charge. The oxygen is picking up a partial positive charge. So we're somewhere along the spectrum where bond forming is happening and bond breaking is happening. So this is approximately what our transition state is going to look like. And then finally, we need to consider our activation energy. So this is the activation energy for step 1. Next, let's consider step 2, which is carbocation formation. So we have our protonated alcohol and water will leave. So this pair of electrons, which used to be shared between the oxygen and the carbon, oxygen says, nope, I don't want to share with you anymore. I'm taking both of these electrons and I'm leaving. So carbon is left behind with a positive charge and water has left. Now, even though we have a positive charge on oxygen, which is more electronegative compared to a positive charge on carbon, this oxygen still has an octet, whereas here carbon does not have an octet. So this is going to be much more unstable than this one is. Therefore, this equilibrium is going to lie to the left. So what does that look like on an energy diagram? If this is the energy of our starting material, then maybe this is the energy of our intermediate. So the carbocation and water. And then it's going to look like this. Now in the transition state, our carbon-oxygen bond is breaking. So our carbon is taking on a partial positive charge, and our oxygen, which started out with a full positive charge, now it has a partial positive charge. So we're not sure exactly how far along this bond breaking has proceeded, but hopefully this makes sense that the transition state looks something like this. And then let's remember that this would be the activation energy for step 2. With step 3, we're looking at nucleophilic addition to the carbocation. So here is our carbocation, and then chloride can act as a nucleophile, sharing electrons with the electrophile. And so that gives us the T-butyl chloride as the final product. And so this lone pair is now this shared pair of electrons. And let's say this is the energy of our starting material. So here's our carbocation. Our product is going to be much more stable, much lower in energy. And then as we think about our transition state, the carbon-chlorine bond will be starting to form. And so rather than having a full positive charge, this carbon will have a partial positive charge. And the chlorine, instead of having a full negative, this is going to have a partial negative. And then this would be the activation energy for step 3. So let's put this all together. Here is the energy of our starting material, the alcohol and HCl. This is the transition state where the oxygen-hydrogen bond is forming, the hydrogen-chlorine bond is breaking, and then this leads to our first intermediate. The product of step 1 is the protonated alcohol plus chloride. So this is our first intermediate, and it is the reactant for step 2. So in step 2, this bond breaks so that these electrons move on to the oxygen. At the transition state, we have this bond is breaking, and so this carbon has a partial plus, oops, sorry, that got cut off, and the oxygen still has a partial plus rather than the full positive charge. That's our transition state, leading to the second intermediate, which is a T-butyl carbocation, plus water, and then, oh yeah, the chloride is still going along for the ride. So here is our step 2. The product of step 2 is our second intermediate, and this is the reactant for step 3. In step 3, the chlorine is adding to the carbocation carbon, and so in the transition state, we have bond forming happening. Instead of a full positive, the carbon has a partial positive. Instead of a full negative, the chlorine has a partial negative. From the transition state, we then arrive at our final product where we have a new bond between the carbon and the chlorine. So from here to here, this is step 1. This is the activation energy of step 1. From here to here, this is step 2. And this is the activation energy of step 2. And then from here to here is step 3. And this is the activation energy of step 3. So the activation energy of step 1, the activation energy of step 3, they are so much smaller than the activation energy for step 2. So step 2 is our rate determining step. Therefore, the overall rate of the reaction depends only on the rate determining step. And so in the transition state of the rate determining step, it's only this molecule that's undergoing changes. Therefore, this reaction SN1, it is unimolecular because of this step. And so this describes the generally accepted mechanism for the SN1 reaction of alcohols with HX.